Welcome back, student. It is Module 2, Lecture 1, Satellite Communication, MECE106A. Shongita Rai, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. Today's content is Satellite Link Design, Basic Link Analysis, Interference Analysis, Attenuation due to rain, Link with and without frequency reuse. The satellite link is essentially a radio relay link, much like the terrestrial microwave radio relay link, with the singular advantage of not requiring as many retransmitters as are required in the terrestrial link. Transmission of signals over a satellite communication link requires line of sight (LOS) communication. But since theoretically three equidistant satellites in the geosynchronous orbit can effectively cover over 90% of the Earth's surface, the need for multiple retransmission is removed. So this is a basic concept. This is the uplink and this is downlink and this is the satellite. And it will be subsequently studied that uplink frequency is always greater than downlink frequency. It has already given earlier 6, 8, 10, 12 gigahertz frequency, because at the time of transmitting we are from the earth, so lot of power can be sent in the frequency, because as the frequency increases, power content in the signal also increases. But at the time of downlink, it is from satellite to earth, so if the frequency is high, then lot of power is needed that is not there in the orbit. For that reason, the uplink frequency is always greater than downlink frequency. Apart from that, when we are giving the signal from the earth, it is of high frequency and lot of power can be accommodated through there, as well as when the signal is going to the upward, the size of the different particles in the air and in the outskirt, they also encounter with the signal, and if the high frequency signal can penetrate easily than that of the lower frequency signal. So, satellite communication specialists, radio and broadcast engineers are in the business of determining the factors required for optimal link availability and quality of performance. This factor can be divided into two broad categories: the conduit factors and the content factors. The conduit factors include such factors as earth space, space-earth path, that is to uplink and downlink effect on signal propagation, quality of earth station equipments, and the impact of the propagation medium in the frequency band of interest. The content factors deal mainly with the type of message transmitted and the devices involved in its transmission from one form to the another for suitability for transmission over a microwave medium. These include but are not limited to satellite functionality, nature and peculiarities of the precise nature of information, data protocol, timing, and the telecommunication interface standards that apply to the service. It is for this reason that a proper engineering methodology is required to guarantee timely deployment and effective and efficient exploitation of satellite communication applications and devices. This in turn must guarantee delivery of objectives for quality, reliability and availability. The remaining part of this tutorial will be presented various component parts necessary for designing a robust satellite link with applicable availability and required signal to noise ratios. The performance of individual links that participate in the connection between the end terminals condition the quality of service, QoS. QoS determines how the quality of the signals at the time of uplink and downlink, and at the end portal how the signal is coming. And bit error rate, BER, very important for digital communication. However, the bar condition the required value of the ratio of the energy per performance bit to the power spectral density of the noise, EB by NO, and how the impacts of the value of the link performance evaluated as the ratio of the received carrier power C to the noise spectral NO, quoted as C by NO, expressed in Hertz. We discuss the parameters that impact link performance C by NO and provides the means to evaluate the performance of an individual link given the transmit and receive equipment in the link, or to dimension the transmit and receive equipment in order to achieve a given link performance. So this is a idea how the link is performed. This is a transmitter and this is a receiver. So transmitter is transmitting the signal from where the receiver will receive through feeder, and it will receive the signal. Now this is a feeder and this is antenna. This is also receiver and feeder and the receiver and antenna. So this is the angle, the look angle, how it is making with respect to the ground. So there are a lot of things. It is the PTX, it is a transmitter output, but this PT is the after feeder, the transmitted power, and there is a gain of the antenna. After multiplying with gain of the antenna, the signal is coming from here. So these are all produces a vital role in the transmission and receiving section. So this total configuration is known as satellite link. The transmit equipment consists of transmitter TX connected by a feeder to the transmitting antenna with the gain GT in the direction of the receiver. The power PT radiated by the transmit equipment in the direction of the receiving equipment, and the performance of the transmit equipment is measured by its effective isotropic radiated power, EIRP. Therefore, how the signal is coming to the space, that is known as EIRP from the antenna. So EIRP is the output from the antenna. So EIRP is effective isotropic radiated power, that is equal to PT into GT in terms of what? PT is the transmitted power from the feeder line and GT is the gain of the antenna. So this is again the figure is showing in detail. So when we are transmitting a signal, there is a receiver, maybe satellite, or from the, when it is satellite, then the ground station is another receiver. So it is a complete process. So it is a cable, then antenna, in the receiver side also antenna through cable or feeder line to the receiving devices. But in between it is wireless system, and as it is showing that they are far apart, not within a meter, they are thousands of kilometers. In case of satellite, it is 34,000 kilometers or less, or maybe greater than this. So it is a huge distance. So lot of distance are there. As the distance are there are a lot of interference in between. There may be air, there may be any another gaseous band, or there may be vacuum, but all are playing a very important role, because subsequently we will study that as the signal travels, the signal is get contaminated to different interference, and their strength also reduces due to different activities. So we will study this. So the pathless L component is coming here. So whatever the signal we are transmitting, that signal is not coming to the receiver, and whatever the signal is coming, that should be sufficient so that it can produce some intelligible meaning to the receiver. So that is the important part, because if the signal is lost at the time of coming through the path, then there is no meaning of this system at all. So this study is very important for understanding total satellite link design. So this is the idea how the signal is deteriorated. So it is a distance showing in 0 to 100 meters in the range it is showing, and it is it is an idea, not exact scenario we are discussing. So it is the receive power. So it is showing that depending on different signal strength, how it is deteriorated, depending on different frequency, how the signal deteriorates. So from the transmitting side, as the distance increases, signal strength deteriorates. So as we proceed, keep on increasing the distance, ultimately there will be some time when the signal is lost totally. So that is the very important part for design any communication in wireless system. So this is the idea. Line of sight, LOS, line of sight is very important because we are always giving importance for wireless communication for line of sight, but always there is maybe line of sight or may not be line of sight. That is very important criteria. Or when the signal is coming, there is a lot of suburbans are there, maybe urban area, maybe rural area, maybe barren area, maybe vegetation, maybe very urban area. So we have to taking care of all those effects. By taking care of all those effects, we should learn, because there is multipath propagation mechanism also there. This is reflection, diffraction, refraction, scattering, and this is due to multipath. Multipath, how it is? Say signal is coming from here. There is lot of peoples are there. People's body is also like a reflector. There is some vegetation is there. It is reflected, scattered. There is also some buildings are there, and there is also line of sight. So when the signal is coming this point in the car, it is the vector summation of all the signal. So if there is only one signal coming directly over there, the effect will be very much different from that of this multipath. So that is also very important for any communication system. The receiving equipment consists of the receive antenna with a gain GR in the direction of the transmit equipment connected by a feeder to the receiver RX. At the receiver input, the power of the modulated carrier is C, and all resources noise in the link contribute to the system noise temperature T. This system noise temperature conditions the noise power spectrum N0, and therefore the link performance C by N0 can be calculated at the receiver input. The receiving equipment performance is measured by its figure of merit G is equal to T, where G presents the overall receiving equipment gain. The following section presents definition of the relevant parameter that condition the link performance and provide useful equation that permit the calculation of C by NO. Now antenna parameters. Gain. The gain of an antenna is the ratio of the power radiated per unit solid angle by the antenna in a given direction to the power radiated per unit solid angle by an isotropic antenna fed with the same power. The gain is the maximum in the direction of maximum radiation and has given by this equation. Gmax is equal to 4 pi by lambda squared into A effective. Lambda is equal to C by F, where F is the frequency of operation. A effective is the effective aperture of the antenna, area of antenna. For an antenna with a circular aperture or reflector with a diameter d, the geometric surface A is equal to pi d squared by 4, and A effective is equal to eta A, where eta is the efficiency of the antenna. Therefore, Gmax is equal to eta pi d A by C whole square. Expressed in dBi, the gain relative to an isotropic antenna, the actual maximum antenna gain is given by 10 log eta pi dA by C whole square dBi. The efficiency eta of the antenna is the product of several factors which take account of the illumination law, spillover loss, surface impairment, ohmic and impedance mismatch losses, and so on. So N is equal to, eta is equal to Ni plus Ns plus N eta plus Nz. The illumination efficiency Ni specifies the illumination law of the reflector with respect to the uniform illumination. Uniform illumination Ni is equal to 1 leads to high level of secondary lobes. A compromise is achieved by attenuating the illumination at the reflector boundaries. In case of Cassegrain antenna, the best compromise is obtained for the illumination attenuation at the boundaries of 10 to 12 dB, which leads to an illumination efficiency Ni of the order of 91%. Now the spillover efficiency NS is defined as the ratio of the energy radiated by the primary source, which is interpreted by the reflector, to the total energy radiated by the primary source. A compromise leads to a spillover efficiency of the order of 80%. Now the surface finish efficiency NF is equal to del G is equal to exponential minus B 4 pi epsilon by lambda whole square, where epsilon is the root mean squared surface error, that is to deviation between the actual and theoretical profile measured perpendicularly to the concave face. So f by d, where the ratio function f by d, d is the diameter of the antenna. So f by d is equal to 0.7, b is the order of 0.9, considering epsilon is of the order of lambda by 13. The surface finish efficiency NF is of the order of 85%. The other losses, including ohmic and independent impedance mismatch losses, are less important. So total or overall efficiency eta, the product of the individual efficiency, is typically between 55% to 75%. So this is showing the antenna diameter and corresponding antenna gain. They are different frequency how they are operated. First 1 gigahertz, the antenna diameter is 0.1 meter to 100 and so on. And for the 2 gigahertz, it is started from below 1 meter, means 0.8, like 0.8 meter and onwards, and so on for 30 gigahertz. So as the frequency is increasing, the antenna size is diameter is reducing. For 30 gigahertz, antenna size is 0.1 meter, and it is gain is very high. Gain is starting from 30 dB. So it is an idea how the gain changes with frequency as well as with diameter. Here eta is equal to 0.6. A is equal to 1 meter antenna at 12 gigahertz has a gain of 40 dBi. This is a just calculation, and say this is a 40 dBi, corresponding it is 12 gigahertz. So if we want 40 dB gain corresponding for 2 gigahertz, it will be size will be 1.5, or maybe it is 5 meter, and so on. It is an idea how the diameter and corresponding frequency changes. So Gmax in dBi as a function of diameter for different frequencies. It shows a reference case corresponding to a 1 meter antenna with a 12 gigahertz. The corresponding gain is 40 dBi. It is giving an idea, nothing much. So radiation pattern and angular beamwidth. The radiation pattern indicates the variation of gain with direction. For an antenna with a circular aperture or reflector, this pattern has rotational symmetry and is completely represented within a plane in polar coordinate or Cartesian coordinate. The angular beamwidth is the angle defined by the direction corresponding to a given gain fallout with respect to the maximum value. 3 dB beamwidth indicate of theta 3 dB is often used. This 3 dB beamwidth corresponds to the angle between the direction in which the gain falls maximum to its half value. The 3 dB beamwidth is related to the ratio lambda by d by a coefficient whose value depends on the chosen illumination law. For uniform illumination, the coefficient has a value of 58.5. With non-uniform illumination at the reflector boundaries, the 3 dB beamwidth increases and the value of the coefficient depends on the particular characteristics of the law. The value commonly used is 70, which leads to the following expression. So theta 3 dB is equal to 70 into lambda by d, that is to 70 into c by fd degrees. So this is the antenna pattern of polar representation, and this is Cartesian representation. In a direction u with respect to the both sides, the value of the gain is given by Gmax dBi minus 12 theta by theta dB whole square. This expression is valid only for sufficiently small angles theta between 0 to 3 dB by 2. Now combining this above equation, we are getting Gmax is equal to eta pi df by c whole square is equal to eta pi 70 by theta dB whole square. If the value of eta is equal to 0.6, then that Gmax will be 29000 divided by theta 3 dB whole square, in which theta 3 dB is expressed in degrees. So the relationship between 3 dB beam width and maximum gain for three values of an antenna is given over there with the effective antenna efficiency 0.5, 0.6 and 0.7, and this is 3 dB beam width, and at the same time its antenna gain is showing. So Gmax dBi is equal to 44.6 minus 20 log 3 dB dBi. So by differentiating this equation, we are getting this expression. So finally, the gain fallout is maximum at the edge of 3 dB beam width. Theta is equal to half 3 dB in above formula, and at the edge of the 3 dB beam width, the value is minus 12 by del theta divided by theta 3 dB whole square. So we are just start to learning how the path loss is affected in the case of any satellite link design. So this is all about for today, and we will continue this session, and this is the references we are concluding. Thank you.